So in order to solve a linear system in MATLAB, here's an example. I'm going to define here a 4 by 4 matrix and a 4 by 1 vector. So that defines a linear system. We have a linear system A times x equals b to solve for x. And since A is 4 by 4, x will also be 4 by 1. So here's the syntax for doing it in MATLAB. A backslash b. That's equivalent to solving the system A times x equals b. And you see that we get the answer here. And in this case, the difference between the two sides, b and a times x, is actually 0 because the answer was integers, so the machine got them exactly right. So one way of remembering this syntax here is that if you did a inverse b, of course a has to stay on the left and b has to stay on the right because of matrix multiplication. But a is sort of in the denominator, if you want to think of it that way, so that's why we use the backslash. It makes it look like sort of like b is in the numerator and a is in the denominator. That's the thinking behind that notation. Okay, if you want to do multiple right-hand sides and you know all the right-hand sides, you can do that in one go. So here's a 4 by 6 matrix. Each column of this 4 by 6 matrix defines a new linear system. So in other words, it's a times x equals b, where each little b is one of the columns of this capital B. So there are 6 linear systems to solve, and it's the same syntax. And now you see that the residual, the difference between the two sides of what's supposed to be an equality, the difference here is small. It's comparable to the machine precision. Now sometimes you have to solve multiple systems where you don't know all the right-hand sides at once. Instead, you know them as part of an iteration. So here's an example of effectively applying A inverse over and over again to a vector that keeps changing. So we give v this starting value, and then inside this loop, we replace v with A inverse times v, and then this is just going to normalize v so its maximum component is 1. Then the next time through the loop, right, this is the right-hand side data and it's changed. So we just keep doing a backslash v over and over again. Now later on in the chapter we'll see that there's a more efficient way of doing this kind of thing, but this gets the job done. Okay, and then the last thing I want to point out is that the difficulty of this problem, or the time it takes to solve this problem, is related to the size of the matrix and the size of the right-hand side. So here's a 5 by 5 system, okay, with this matrix A, and B just a vector of 1s. So for this 5 by 5 system, it takes essentially no time at all. I mean, that's as little time as the machine can measure. So here I'm going to do an experiment where I let the size of the matrix go from 100 up to 1,000. And I'm going to do 10 solves for each matrix so that I just kind of average out fluctuations in the timer. All right. So on my machine, this is all very fast, even up to 1,000. So you can see that the time increases as n increases, but it's not necessarily a smooth, easy pattern. So if you go from 200 to 400, that looks like a factor of about 4 or 5. If you go from 400 to 800, again, that's something like a factor of 5 or so. So later on, we'll see how this effort might scale with n, but if you think about it, the size of the matrix is n squared. So if you go from 200 to 400, you've already got twice as many or 4 times as many numbers to deal with. So it's not surprising that the time goes up by at least a factor of 4.